So we're going to solve log equations using what we know about properties of logs, along with this last new property that we're going to introduce, right? So we learned about just how to condense and expand logs that are just a part of an equation. Now we're going to take this to the next step, and we're going to say, if you have a situation where you have an equation, right? That's what's going on in this particular example here, right? We have this equation, and we have a log on the right and a log on the left. Okay, that's what's going on here. They have the same base, which I'm calling b. Okay, meaning, so really what we're saying is, if there's only a log on the left and a log on the right, there's nothing else floating around on the outside. Really what that means is that the inside of the equations have to be equal. So this is kind of analogous to, we did one back for exponentials where we said if you had something like 2 to the x is equal to 2 to the 4, base on the left equals base on the right, nothing else on either side of the equation, that means that x has to be equal to 4, right? The exponents have to be equal to each other, right? Well, if we're talking about logs, we're really talking about exponents. That's what logs represent. They represent the answer is an exponent. So we're really saying exponent has to be equal to exponent. X has to be equal to y, right? So if you come down to this problem, I think it'll illustrate that for us really nicely. Okay, in this problem, I'm looking at the situation and I say log base 3 of an expression equals log base 3 of an expression. So because this and this are the only things that are on each side of their equation, the log expressions, what we can really do is just disregard those. What's inside of the logs, the x plus 1 and the 7, they have to be equal to each other, or these logs cannot be equal to each other. So our answer here is 6. Okay, so there's going to be these examples, these really nice problems where we can just say if it's log on the left, log on the right, set them equal to each other and solve, we're finished. Okay, so once we come down to some of these other problems, the same situation is going to apply. Okay, so I'm going to actually not do these two examples. I want to highlight some stuff that happens in some in the next slides examples that are very similar to these. Okay, so in this example, let me get rid of my joke about pizzas. It has nothing to do with our problems. Okay, so the same thing's happening in problem number 1. Okay, I'm going to say log 5 on the left, log 5 on the right, nothing else on either side. So that means that 2x minus 7 has to be equal to 3x plus 1. Okay, and I can solve this. If I subtract the 2x over, I get x. If I subtract the 1 over, I get negative 8. Okay, so here's where things get a little funny, right? This appears to be the answer. Okay, here's the issue that we run into. Okay, if I were to ask you, this is completely kind of separate. What's the log base 2 of 3? We know the answer. I'm sorry, the log base 2 of 8. Just gave away the answer. Okay, the log base 2 of 8 is 3. Because 2 to the third power gives me 8, right? When I say log base 2 of 8, I'm actually asking the question, 2 to what power gives me 8? The answer is 3, okay? So if I were to change this slightly and say, what's the log base 2 of negative 8, okay? Now all of a sudden we run into a problem, because again, here's what we're asking. I'm saying 2 to what power gives me negative 8, right? And so what I'm asking you to do is, repeatedly multiply 2 by itself some number of times, and I want the answer to be negative, right? Multiply a positive value by a positive value by a positive value by a positive value some number of times, and give me a negative answer. That is impossible, right? So we actually have the situation where if you try to take the log of a negative number, there is no answer, right? And that actually kind of makes sense with what we were saying is that when we start graphing logs in a little bit, or I'm sorry, when we start we were talking about exponentials, we were graphing exponentials, we said there was an asymptote, right? There's this value where the range stops working, and that was in this case 0. The output values for exponentials have to be bigger than 0. Right? So this situation where we have this negative 8 in our problem, we actually have to go back up to the original problem right here and see if I'm taking the log of a negative number, and in this case I am, right? When I plug in the negative 8, I get negative 16 minus 7. This becomes the log base 5 of negative 25. And the log base 5 of negative 25 does not exist. So this is what we call an extraneous solution, okay? Which we've seen before with radicals, and we've seen before with rationals. Sometimes a value looks correct, but when we plug it back into the context of the problem, it doesn't make any sense. So we're going to actually say for this first example that there is no solution to this problem. Okay, so that's one really major thing you got to watch out for, is that when you're solving log problems, you need to take your answers, plug them back in, and if there's anywhere in the original problem or in any subsequent problems below that you're running into the log of a negative number, that answer does not apply, right? It is not a good solution. Okay, so let's take a look at these last two examples. Okay, to start seeing where our properties of logs might come in, right? If I'm trying to get the situation where I have log on the left, log on the right, well, this doesn't have that, right? This 3 and this 2 floating around outside of the log means that I do not have a one-to-one function. I don't have log on the left, log on the right. So what I'm going to do is I'm going to use the property of log that says if you have a coefficient in front of a log, you can make that the exponent of what you are taking the log of, which means I can rewrite this as log base r of x to the third power. And I can do the same thing here. I can take this 2 and bring it in as the exponent of 8. It would be the log base r of 8 squared. Okay, so I'm going to come over here where I got some space. Okay, I'm going to say this is now the log base r of x cubed is equal to the log base r of 64. Now I have my ideal situation, log on the left, log on the right. That means x cubed is 64, which means that x has to be equal to 4. Okay, and again, I'm going to do a quick check. I'm going to come over here with my 4. The only place I could plug it into a log is right here. I'm taking the log of a positive number. That's a good value. Okay, so here's your last problem. Okay, so we're going to say log base 9 of 4 plus 2 log base 9 of x. Okay, so here's that situation happening again. A coefficient on the outside of a log becomes the exponent on the inside of the log. So this second one's going to look like the log base 9 of x squared. Right, and then I'll bring this one down. Okay, and so I still have a bad situation where I'm looking at this and saying, okay, 2 logs on the left. I don't want that to happen. I want there to be 1 log. So we had a rule that said if you have addition between logs that are of the same base, which that's true for us, you can multiply what's inside of the log. So that's, in this case, the 4 and the x squared can be multiplied together. Log base 9 of 4x squared. So I multiplied them together and applied them to 1 log equals 0. Okay. So I still don't have this ideal situation, log on the left, log on the right. Okay. But what I do have is a problem that I can use a log conversion on. So don't forget, because we have this new property about log conversion, which basically says this is the base, this is the exponent. 9 to the 0 power is equal to 4x squared. Okay, and so now this is a very easily solvable problem. If I say this is really means 1, 9 to the 0 is 1. Okay, and if I divide over the 4, it becomes 1/4. Okay, I'm going to square root both sides, okay, and I'm going to say x is equal to plus or minus the square root of, oops, not the square root of anymore, x equals plus or minus, when I take the square root of 1/4, I get a 1/2. But again, when I come back to my original problem, right here, I can't have a negative value for x, so I'm actually going to adjust my answer and say, you know what, I'm not going to take the negative version, and we're just going to leave it as 1/2. There's only one valid solution for this one, and that is the 1/2. So we threw away the negative because that made our problem that problem was extraneous. It made our problem have no solution. Okay. So here are just some final examples. I'm not going to spend too much time on these. Oop, let me get rid of my screen here. It's adding in some stuff. Okay. All right. So this is just some quick stuff. I'm not even going to go through all these problems. I just want to show you some of the variety that you might see. Okay, so our first example, very similar to what we just did, right? This is going to say the log base 4 of x squared equals the log base 4 of 81. Log on the left, log on the right. That means that I can say that x squared equals 81. I can square root both sides. X is equal to, again, plus or minus 9. But here it is again. I can't have a negative number right there, so I'm going to throw away the negative version, and I'm going to say that x is equal to 9. So almost identical to what we just did. Okay. Next problem, I'm going to be able to go right to saying if it has log on the left and log on the right, I can set what's inside equal. Okay, 4x is equal to 32. Okay, this is a quadratic. So in this case, the only variety that I'm adding to the problem is that you have to solve a quadratic equation. So I'm going to say x squared minus 4x minus 32 equals 0. Right, let me come up here. Okay, I can factor this expression or quadratic formula, whatever you prefer. This one factors really easily into x minus 8 and x plus 4. Equals 0. Okay, and so it looks like I get two answers out of this. I get x equals 8 and x equals negative 4. And so again, we got to consider, is this a good value? If I plug in an 8 here, this says 64 minus 32. That's good. That works. If I plug in a negative 4 here, it says 16 minus negative 16. That is also positive. Okay, so just this to highlight, just because you have a negative x value does not mean you're going to throw it away. This negative 4, when I plug it in right here where there's some x values, gives me a positive number to log, so I'm going to actually keep that one. Okay, so your bottom problems are going to be pretty much the same. This problem, I'll just show you the first step. When I combine, it says the log base 6 of x times x minus 5, right? And then you can set these equal to each other, and it's going to look very similar to the problem above it. This is going to say x squared minus 5x equals 24, right? And that is something that you can solve. And in this case, you are going to throw out, just in case you finish this problem, you will throw out one of your solutions, which I believe is -3. Okay, so you will throw out a solution because you can't have any negative values because of that x right there. Okay, so your last problem, the 2 is going to come inside. It's going to apply to the entire x plus 3. So it's going to say x plus, well, let's do it correctly. The log base 7 of x plus 3 squared equals the log base 7 of 169. Okay, so now I can set the logs equal to each other. It's going to say that x plus 3 squared is equal to 169. And be careful, you don't have to expand this out. You can just square root right now. Okay, so it looks like that x plus 3 could be equal to 13. Okay, or remember it's plus or minus when you take the square root. Oop, not log anymore. Okay, talking and writing at the same time. X plus 3 could be equal to -13. And so here are my two answers. It looks like I get 10 and I get -16 as possible values, but I'm going to throw one of those away because, get rid of this, okay? When I come back up to my original problem, when I plug in a 10, I'm fine. I'm taking the log base 7 of 10 plus 3. That's good. But when I plug in the -16, it says -16 plus 3. That is not good, right? So this value, -16, gives me a negative log, and so I'm going to throw that one away. Okay, so I'm going to end here. There's a couple more examples that I'm just going to throw into the last video, and then we will be done with solving logs.